Start. Okay. So last time, we're trying to figure out what is the structure of the atom. And up to Rutherford, okay, there have been models being proposed, but every model had some problem or the other, like it was not perfect, right? So some phenomenon got discovered that actually helped in figuring out the structure of the atom, or that either disproved the previous structures or like it added on to it. So the first one was related to electromagnetic radiation. Specifically, Max Planck was a scientist who was experimenting, like who dealt with all the quantum stuff. Okay, so his one particular theory about, or his like findings about black body radiations is what contributed, like that was like step one towards figuring out structure of the atom. All right, so what do you mean by black body radiations? So last time we talked about electromagnetic radiations, right? So from now onwards, every time you come across radiations, it means that it's pure light, pure energy. Like light energy can be used interchangeably in this context. Light is a form of energy. Another shift is that every time someone talks about light, you need to think of the whole range of light, the whole electromagnetic spectrums. It's not just the light that you can see, it also includes UV radiation, infrared, X-rays, like the whole spectrum of it. Okay, so that's light and energy. So black body radiation. What do you mean by a black body? I mean, the
A
words.
body containing dark matter?
Oh, no, it's not that
Oh, I'm
complicated.
just confused.
Yeah, it is literally a body that is black. Okay, so what's so special about a black body is, do you remember how light works? Like how colors work, basically, like how you can see different colors. Yeah, any of you, Smera or Ritu, how do you see different colors?
There's like a range that's visible to you, and white light usually splits into like different colors and they get like dispersed by some amounts that you can see those.
Okay, so what makes something colored? Like if I have this pen, what makes this part white, this red strip, and this part green? Like, what's the explanation behind that?
Maybe the lights reflect like that.
Yes, correct. Now, what's the difference between light reflecting on the green part and light reflecting on the white part?
So wavelengths of the colors are different.
Very good. Absolutely. So this part, I mean, I think you guys have studied about it much, much, much earlier, like in 7th or 6th. Are you familiar with it?
Ma'am, I think we also did this in physics.
You did?
Yeah,
Right.
when we
Oh,
did
yeah.
the eye chapter, no? We had
Right.
the color
Okay.
spectrum.
You had it. Right. So,
Yeah.
yeah, like how you see different colors is that color's wavelength is reflected and all the other wavelengths are absorbed. That's how you see colors all around you, right? And that reflected light enters your eye, and yeah.
Ma'am,
Yeah,
also for the black body part, I think black does not reflect any light, right?
I was just coming to that. Like how, like, yeah, what makes something black? Like what's happening to light in that case?
All the light is absorbed.
Yes, correct. So there's none of the colors reflecting back, all the colors are being absorbed. So that's how, like roughly, very simply in one light, that's how, one line, that's how you describe black bodies. That's the color black. Okay. Now, Max Planck took a black body, like literally any object that's like extremely black. Before we get into Planck's experiments, right? Ideal, perfectly black bodies do not exist in the universe. So you have, yeah, Ritu?
I had it out, but carry on. I'll ask after like you're done.
Okay. So perfect black bodies in the sense you won't have any body that absorbs all the light that is thrown over it. Nearly black exists. Like as an argument, like I can show you this is a black marker. You can see that, oh, there is something here. Like you can recognize as a black object here, right? But is this perfectly black? Like, do you see all the light being absorbed?
No.
So you can see there is like a slight shine right here. You can see there's some amount of light being reflected off of it. So that way, it's not just the color, also the texture comes into picture, and the material comes into picture. So you cannot have like, yeah, a perfect black body doesn't come in, is does not exist, but you can come close to it. And that's what a whole bunch of scientists have also kind of done experiments on. Let me show you. Where is this thing? Oh yeah, there you go. So yeah, so the way people have tried designing is have a black object, like a black sphere. If it is colored black, yes, that's like half your work done. Black absorbs all colors. Now, to make it further perfect, what people did is it's a hollow sphere and make a tiny hole in it, really small hole in it. So what this ensures is whatever light is getting in is, and make the internal material such that whatever, like don't make it smooth. So that way it gets scattered inside. So that way you can ensure, again, everything is being absorbed. Nothing is, getting out of this body as such. So that way people have tried designing like black bodies. You have near perfect, you can come close to it. And similarly, people have experimented with materials also. There's a whole Wikipedia page about black bodies. How many of you have heard of this thing called Vanta black? I was there in the media.
I was just gonna mention that it
Yeah.
absorbs like 98% of light, right? I think.
Correct. Yes. It just looks like random void in the space in front of you. Like, yeah, it's called the blackest black. So Vanta black was the most recent material that people have, that one person has designed with using some chemicals like an alloy of nickel phosphorus, and there's also carbon nanotubes also involved somehow. I don't know the exact details, but yeah. Lamp black, which is basically a form of carbon, pure carbon like soot that is coming close. So yeah, all these are near perfect black bodies, but yeah, ideal black bodies don't exist. Okay. Now,
Or maybe they do exist, but we just can't see them because they absorb all the.
you just can't see them, but you should be able to feel them and figure out that
Oh
something
yeah, I
exists,
forgot
right?
about.
Yeah. Maybe you could say black holes are a form of black body. They just absorb everything, but that's, yeah, that's like further discussion. So
I had it out.
yeah, Ritu.
So nothing actually has color unless light is reflected on it. So could you say like by default everything is black?
Yeah, kind of. I mean, yeah, you need to shine a color. I mean, some light has to, like, even if you have a tiny bit of light, you kind of can perceive color on it, right? Like, even in the dark, even if you switch off all the lights, you can still figure out if something is like bluish or reddish in color. So, yeah, I mean, if you have zero light, yes, it's complete black. Everything is black. Yes. Yeah. Okay, now coming back to black bodies. Okay, another thing about black bodies. Now we're talking about black body radiation, right? What is this black body radiation? Hot objects emit electromagnetic radiation over a wide range of wavelengths. This is a fact. Like if something is hot, you can feel that hot because it is radiating some amount of energy. So the best way I can make you guys visualize this is, think of an iron sphere. At room temperature, like, oh yeah, okay, it's not very cold. It's kind of cold. You don't feel the radiation as such. Heat it. What happens to iron when you heat it to like fairly high temperature?
Becomes red hot.
Red hot. Very good. There's a word, red hot, right? Like, why do you call it red hot iron?
Because when heated, it looks like it's red in color.
Yes, correct. So basically, it's emitting radiation of in the wavelength which is reddish in color. So that's why red hot iron, it starts looking like reddish in color. If you heat red hot iron to even higher temperatures, what does it turn into?
Magma, I guess, like some sort of liquid lava sort of substance.
Let's assume for our experiment, we are also controlling the pressure so that iron doesn't melt. So it's still the iron sphere, just that its temperature just keeps going higher and higher and higher. Red hot के बाद क्या होता है?
It becomes white hot.
White hot, yes. And what does that mean? Like red hot matlab it's giving out red ka wavelength. What does white hot mean?
All colors.
It's slowly red se chalu hoke, it's covering the whole range of wavelength of WebGear, all 7 colors. That's why it looks like white hot, right? And if you further heat it up, then what happens?
Will it eventually turn violet?
Yes, Kaveri. Like, I am not sure if who's heard of this, but the sequence is this: like, first you have red hot, then turns into white hot, and then there's something called like it starts looking blue in color. Blue hot. Like, this is the sequence for classifying stars also. Like, instead of white, you have yellow, I think. Yeah. So if anyone's does like fun astronomy reading, like this, how you classify stars. Yeah, you have like weird alphabets, numerals, and all that. But roughly temperature classification, you have red, white, and blue stars. Okay, that's because as temperature increases, this is what's been happening. So what can you infer about the wavelengths from this? Yeah, Ritu mentioned blue giants. Yeah. Okay. What happened to the wavelengths?
Reduces.
Yeah. So wavelength is decreasing. So as temperature increases, the wavelength of the emitted radiation decreases. It's like shifting from higher wavelengths to lower wavelengths, right? Okay. So that's what it says. At high temperatures, a larger proportion of radiation is in the visible region. As temperature is raised, a higher proportion of shorter wavelengths is generated. So as you increase the temperature, the radiation that is emitted from that heated object keeps decreasing. Thus, the intensities of radiation of different wavelengths emitted by a body depends on its temperature. Right? Like, again.
Do we have to note this down?
No, don't have to. I'll let you guys know what to note down. Yes. So, thus the intensities of the radiation of different wavelengths emitted by a body depends on the temperature. Clear about this statement? Yeah. So every object in the universe, as long as there is some amount of temperature associated with it, be it high temperature, low temperature, it is always emitting radiation. So like,
excuse me, ma'am, I have
yeah.
a doubt.
Mm-hmm.
So can we just like change the color of an object just by changing the temperature?
You will also be changing other properties along with the color. So not recommended, but theoretically, yes.
So
Miss,
if
I
I have
had
a
it
blue
down.
bottle,
So if you have, yeah,
blue
so if you want to, if you heat it to the point of changing its color, it's not just the color, like something else also changes. Bottle's gonna melt, it's gonna burn, other stuff's gonna happen. Okay.
Ma'am, I did not understand the point where it said as the temperature is raised, a higher proportion. That one, I did not understand that. Can you just explain it again?
Yeah. So as the temperature is raised, so as the temperature is raised, as you increase the temperature, like think of the iron ball, you're increasing it, higher proportion of radiation of shorter wavelengths is generated. So this is like indirectly telling you that as you increase the temperature, the radiation that is emitted from the body, right? That radiation's wavelength keeps decreasing. So at a particular temperature, let's say it was red hot. As you keep increasing it, the wavelength as it decreases, you start getting, up to like blue hot. That's what it's saying. Higher proportion is like, yeah, it's a wide range of wavelengths are emitted, but that's what you can see. Like something looks white because the whole visible range is emitted. But as you keep increasing it, slowly it starts turning blue because blue dominates over all the other colors. So higher proportion of shorter wavelengths is generated. Correct?
Temperature is inversely proportional to wavelength.
Yeah. So the temperature is inversely proportional to wavelength of the radiation that's emitted. Basically, yeah.
Ma'am, I had a question. Like you said over here, like red, white, blue, like these are the degrees at which like you can measure how hot it is basically. So like when the object reaches its boiling point, after blue it will directly melt instead of showing any color.
Now, actually, it depends on the object. Like some objects would melt when it's at between red and white itself. Like phase change also depends on the pressure that the object is in, and like a lot of other factors. But this is purely the radiation that's emitted at that particular pressure. So it's not related to phase changes or chemical reaction or anything else. Like it's purely, oh yeah, you have this temperature, okay, this object is emitting this wavelength that way.
Oh, okay.
Ma'am, so then if like by some miracle it doesn't like melt by blue, could you make it like invisible after that?
Yeah. And yeah, it'll be invisible to us. It's gonna emit radiation and shorter wavelengths, X-rays, gamma rays, all of that. Smera, you had a doubt initially?
It got answered with Rishit's question. Like my doubt was how come we get white first and then blue, but then later
Yeah.
understood.
So you have like red plus maybe IR, the heat wala wavelengths, and then slowly maximum is like visible. That's where you see it as white, and then slowly the whole range shifts shorter and shorter that way. So we'll get deeper into this. Like this is what we're going to study. So this is like the thing for any object. When you heat it, it emits radiation, and it's not just you feel like you heating it. Every object in the universe is emitting radiation. You say something is cold, like the concept of cold exists because of your feelings. Like if something is at a lower temperature than you call it cold. If something is at a higher temperature than you call it hot. But technically, like all the objects in the universe are hot. They're just like hot, very hot, less hot. Like every object
So
associated
it's
with a
all
certain
relative.
temperature, yeah, it's all relative. Yes. Okay. All right. And this, we discussed black body is an ideal body that absorbs and emits radiation of all frequencies uniformly. So it can absorb everything. It's not selective in what it's absorbing. And then it just emits everything uniformly. So in practice, such a body does not exist. It's like an idealized version. You can come close though. A black body is in thermal equilibrium with its surroundings. What do you mean by thermal equilibrium?
That means
Its
the
temperature
temperature
is
is the
equal.
same as the surroundings.
Correct. Absolutely. Temperature is same, which is to say it's not doing any heat exchange with the surroundings. Like whatever heat it absorbs, it's like emitting the same amount. So net is 0. Here. Yeah, so that's what it says. Like it absorbs all radiations, it emits also all radiations. Now, what did Planck find out? So Max Planck, this guy, he studied black bodies. He heated up a black body and then he recorded what all wavelengths is it emitting out. And then he did a bunch of experiments. Oh, if I change the temperature in this way, then what is happening to the wavelength? If I change the temperature in the other way, then like what is happening? So intensity of light, so basically like the brightness, how much light something is emitting, absorbing, emitted by a black body depends only on its temperature. Another thing you guys need to be careful is intensity is very different from its color and other things. Intensity only tells you how bright or dim it is. So you can have a bright red, so red wavelength, high intensity, a dim red, again, same wavelength, just that the intensity is low. So intensity is very different from, yeah, your radiation's energy, your frequency, your wavelength, and all of that. Okay.
Ma'am, I have a doubt.
Yeah.
So is intensity like similar to concentration of wavelengths?
Yeah. So intensity, like the measure of intensity is the amplitude of the wavelength. So we discussed last time, right? You can have high amplitude. You can have at the exact same wavelength, low amplitude also. Okay. So intensity is basically, okay, what's the amplitude? So at a given temperature, the intensity of radiation increases with the wavelength, reaches a maxima and decreases with further increase in wavelength. Okay, now we're getting into the findings of Planck. This I will show it to you guys live. So when Planck actually did the experiment and he put the did the recordings. So on the y-axis of this graph is the intensity. So this shows the intensity, spectral power density. Another way to say intensity. Okay. And on the x-axis, you have wavelength. So at a particular temperature, okay, the default that is set, black body temperature, you can see here is 5800 Kelvin. Means in Celsius, how hot should it be? Do a quick conversion. You can give it roughly also, just do a mental calculation.
5500 Celsius.
Yeah, somewhere around between 55, 5600 Celsius. Yeah. So imagine like those are the ranges of temperatures that we are working at with respect to like black bodies. Yeah. So, oh, you're given the scale also here, like Earth's temperatures, your room temperatures are like, you can't even measure here. Light bulb is basically the temperature inside a light bulb. So you have the filament, right? So the filament needs to get at this particular temperature for it to, like be visible. And then slowly increase it. You can see that the sun is at around 5800 Kelvin, which is why you can see the maximum intensity lies in the visible range. That's why you can see sunlight as, white light. Here. Anyway, so coming back to this, yeah. So Planck, he took a particular black body at a particular temperature, and then he measured, okay, what all wavelengths of light are we actually getting and at what intensities. So this is the kind of graph that he plotted. Okay, this is the experimental graph that he plotted. So let's take a snapshot.
He took a black body means what? Like black bodies are theoretical, right?
No, but you can come close to it. Like, yeah, obviously he didn't take a perfectly black body, but he took a near black body. So I've showed you the design, right? Like how people have tried creating black bodies. He took one of those. Okay. Then when you change the temperature, Planck found that, let's show the values also. So the maxima was at 0.5, the value here. When you increase temperature, how do you expect this graph to look? Like, what are the predictions?
The
Color spectrum will increase.
magnitude of wavelength will decrease if you increase the temperature.
Yes, wavelength will decrease, which means that this point should go, it should shift towards the left. And let's see what happens to the intensities there. So when I increase it, you can see that a slight, okay, this is going outside the graph, so I'll just do it till here max. You can see that from 0.5, it has gone to 0.487, which means that wavelength decreased, which is what we predicted. And you can see that the intensity has gotten bigger, like you have more intense light at shorter wavelengths, which makes sense, right? Like if you heat something, it gets hotter, like you can feel the heat like properly. It's pretty hot. So I'll
At what color is it at?
this you're getting, again, this is going to look white. It's going to be sort of like a bluish light, bluish white, not like a creamish white. It's more of a bluish light. The reason is that it's not purely blue. It's got, like, imagine your fluorescent tube light, right? It's not warm, like you don't have a yellowish tinge to it. It's more bluish. So the reason is that you're getting, like, the whole visible range is like pretty high intensity, so you'll be able to see all colors, but this particular wavelength dominates, like the bluish tinge dominates, sort of. So I'll reduce the
Ma'am, I have a
temperature.
question.
Yeah.
How do we know the temperatures of the sun and like Sirius A?
There are methods to calculate it, like based on the distance and based on the temperatures that you feel here. And of course, like there's been space missions and all also, right? That's a whole another topic. Like, I'll have to get into that. Okay, so when I reduce it, you can see that the maxima is shifting. Like at higher temperatures, you had more intensity at shorter wavelength. Lower temperatures, the peak has shifted, but it's still, it's not like one specific wavelength that you're getting. You're getting like the whole range of it. There is radiation of, like ultraviolet, infrared radiations. There are like radio waves also being emitted, but you can like hardly detect them, like the very, very low intensity. So again, the radiation is being dominated by your yellow red lights. Still in the visible spectrum, but like somewhere over here. Yeah.
How do we say that according to the graph, how do we say that the wavelength has decreased? Because the x-axis ka extent remains the same, right?
No, the maxima has decreased. Like at lower temperature, it was at 610. At higher temperatures, you can see that the maxima is decreasing. So the wavelengths that are dominating is decreasing. Overall, all the wavelengths are being emitted.
That's the wavelength. That stands for the wavelength.
Yeah, the x-axis is your wavelength measurement. So at the maxima, at this peak, you can see that the x-axis is at 0.542, like 0.542 wavelength is having maximum intensity as compared to other wavelengths. That's how you read it. Okay. So yeah, now this was an extremely important finding, like this particular finding of Max Planck was extremely important because it was contradicting a lot of things. Like it was contradicting everything that people theorized about light energy back then. Okay, so the current theory was that light is a form of wave, electromagnetic radiation, light waves, and wave form of light also, what do you call it? It fit, or it explained some phenomenon of light. Like, have you guys heard of interference and diffraction?
No, man.
I haven't.
No? Yeah, like it's not there in your syllabus yet. That's why I was wondering if any of you have come across interference, diffraction, anything like that. Okay, so there's some phenomenon of light, like interference is the most famous, popular one, and it's like one of the pretty ones. So interference is basically, like, again, it's an experiment that someone called Young had conducted. So what he did was he took a screen and poked two tiny holes through it. Okay, tiny holes, two holes. Important that they need to be two holes. And then he put a light on this side. Now, what do you expect to see on the other side of the screen? Any predictions? Like, what do you think you'll see on the other side?
A shadow except for those two holes, light passing through those two holes.
Can you describe the shadow, Kaveri?
I mean, the entire box is a shadow except for the two holes where the light was passing.
So are you saying that, okay, let me just draw it for convenience. So let's say we have light source here and we have a screen here, and in the screen there's two tiny holes kept. Okay, I can't erase it with the eraser here. Let me just change color. Oh, there's two holes over here. Okay, so now, yeah, can you describe the, like, what you see on this side, Kaveri? You said you see light. So do you find like two dots like this, or what exactly are you saying?
Roughly 2 points where the light is passing through.
Okay. Others, what do you think? Does this make sense? Is she right? Sanat, Adat, Ritu, Vishak?
No idea, ma'am.
No idea at all. But at least like
No.
Kaveri has tried, right? Like, you know how lights and shadows work. Like, this is a setup that you can easily create in your home. Don't use a candle.
I didn't really understand the question. Can you just repeat it?
Simple. You see this setup here, right? It's dark all over. I have like a wall or something over here, and I put a screen over here. And in the screen, I have two tiny holes, like a millimeter wide holes that you can see, the two black lines here. Then on the other side of screen, I put a source of light. Like, it does, usually candles are used, but you can also use like a torch light, any source of light. Now, my question is, what will you see on the other side of screen? Like, what will you see over here?
Is there a hole in that side too?
No, it's just a plain screen. The holes are only here. There are two holes here.
I think since there is no light inside the thing, it will just reflect and it won't show anything.
Okay, Rishit saying nothing. Kaveri said it'll show like wherever the
I
holes
guess.
are, two lights here. What else?
There might be like pinpoints of small, like a small circle of light, maybe. Like
Like
what
a
Kaveri
single
said.
circle. Okay, or two different.
Two different, two different.
Two different. Okay. Okay. Cool. This makes most sense, right? Like based on what you know of light, light travels in straight lines. So like here you have a screen, light cannot travel here. So wherever light can travel, you should see like two straight points of light, right? Maybe they'll be slightly bigger, because light also diverges. This way it's radiated in all directions. But you will be surprised to know what actually you end up with is a pattern like this. This is what you end up seeing on the screen. So this pattern is called interference pattern. And this, along with another phenomenon called diffraction, which is like basically bending of light. So these two.
Something.
Ma'am, I
Sorry,
can't
miss,
see
what
what you
pattern?
drew. Yeah, it's not showing whatever you drew. Just
Oh, I'm sorry. I was sharing the wrong screen. Oh, there you go. Yeah. Instead of two pinpoints of light, you end up seeing this pattern.
But how?
Yeah.
So
If there is no
this,
hole, how can you see that?
so this is the best one that actually showcases it. So these two are the holes. And on the other side of screen, you can see alternating bands of light and dark. So the reason for this, like this particular phenomenon where you make two beams of light interact with each other through these two thin holes, this is called interference. And this particular pattern is called interference pattern. The calculations behind it, the physics behind it, you will study it in your grade 12 when you study about in the light chapter. But roughly, this is what's happening, okay? So this cemented the theory that light is a wave. So if you have wave 1 and you have wave 2, so light from here, this is wave 1 and this is wave 2. Now when they interact with each other, again, light radiates in all directions, right? So you have light's actual pathway is something like this. Now when the light is like interacting with each other, when two different waves of light are interacting with each other, either they can interfere constructively. So you have something called constructive interference. Which is basically it's constructive. So they add on to each other. So this happens when the crest of wave 1 coincides with the crest of wave 2, and they both end up being like a brighter wave. Or, yep.
When the part that after where you do the blue line, after that touches, so I get that they are having the constructive interference.
Yeah.
But before that, the waves are not even in contact with each other, the light waves. So how
this is how I am like. Again, I can't animate this, right? So basically, what is
the Google images?
Oh, this one. Okay. So that's what, like, I'll come to it. First, I'll explain the phenomenon and then we'll get into this. Okay. So either they can have constructive interference or they can interact in something called destructive interference. So destructive interference, again, the hint is in the word destructive. they destroy each other, and this happens when the crest of wave 1 coincides with the trough of wave 2. So this goes up and then this is going down. So basically they cancel each other out, and there is nothing, there is no wave, because they're exactly canceling each other out. And depending on at what point they are interacting with each other, it is going to range from completely constructive interference to destructive interference. It's either like double or nothing sort of a deal, and everything in between. So the dark bands that you see here in the interference pattern occur when there is destructive interference of light. So light wave 1 is canceling out light wave 2 because they're behaving oppositely, like one is going up, the other is going down, so end up not going anywhere. And the brighter bits is when they're interfering or interacting constructively, so when there's constructive interference. So one is going up, the other is also going up, so they basically add on to each other. Yeah. So this is like basics of interference. You are going to study about it a lot more in detail in physics. But this sort of occurrence, like alternating bright and dark, can only happen when you have two waves interacting with each other. It doesn't happen when light is a particle. Like only like interference is a phenomenon of waves. The same thing happens with sound waves also. When you look at waves and motion, when you do these topics in physics, it will be explained in detail. You do a lot of numericals based on this also. So the phenomenon of interference is explicitly a characteristic if that particular thing is a wave, sound wave, light wave, whatever it may be. So based on this, previously it was thought of that light is a wave, and it was accepted. Everybody was like happy, established, light is a wave. That's why light has wavelength and all that. But if you went with the explanation of light being a wave, so as per the classical theory, like you can see here, ideally, like theoretically, black body graph should look like this, where, you know, it should be as the energy, like as the temperature, like at any given temperature, as the wavelength is shortening, like the intensity should go on increasing. So according to the classical theory, according to whatever was believed at that point of time, this should be the case. But obviously, practically, when Planck measured it, it was not. You had wavelength of particular particular wavelength and high intensity, and none of the rest, like lower intensity of the rest. So there was like a particular maxima associated for each temperature. So this was,
theory and all that.
that's okay. So basically it's okay. Like this goes into extreme quantum mechanics. It'll be difficult to cover. But the thing is, the main point of all of this is that if you consider the wave nature of light, like if you believed that light is a wave, which is what we've been working with so far, then this should have been the graph of black body radiations. So the intensity versus wavelength graph. But this is not the graph of black body radiations. This is the actual experimental findings that Planck had. So Planck was trying to come up with an explanation as to why are these radiations behaving in this way. Okay, so yeah.
For this classical theory, the black one, so so in this graph, then the black color should be the brightest, right? Or it's like not visible to us, but technically it should be the brightest, right?
Exactly. Like that's what should have been the case. Like that was the theory at that point of time. but obviously reality did not fit the theory that they have. So they needed to figure out, okay, then what is the correct explanation for it? Like, what is the correct behavior? How do we predict this? Okay.
If they're different graphs, then how come they're at the same temperature, like 5000 K?
No, so this was like what was theoretically predicted. This is the actual graph at 5000 K.
Oh.
Obviously, their predictions were wrong, which means that their calculations or assumptions or whatever theory they were following in the first place, that itself was wrong. Okay. So Planck was like scrambling around. He was like trying to find what is the explanation for this, like how can I get these values theoretically also, like what formula should I use, what assumption should I use. So yeah, so Planck said, yeah.
What is ARB?
ARB?
Intent.
Arbitrary values, approximations. Okay, so and then Planck said, okay, let's assume. So what Planck assumed was that, so results of black body radiation could not be explained on the basis of wave nature of light. So Planck assumed that absorption and emissions occur from an oscillator. Like at that point of time, like obviously structure of atom was not completely established. This is what Planck worked with. He said that, oh, the black body was made of a lot of particles and the particles are oscillating. So he called them oscillators. So basically, like if you look at the actual reality, he referred to the atoms on the walls of the black body as oscillators. So he said the absorption and emission, like the things that are absorbing and then emitting back the radiation, they're occurring from an oscillator, and that if they're oscillating, they're moving, they will have a particular frequency associated with them. So their frequency changes on interaction with the oscillators from the electromagnetic radiation. So he's saying that, okay, so the absorption and emission, like this is the explanation that he gave. They're occurring from an oscillator, that is like the atoms on the walls of the black body. And when you change their temperature, they're interacting with the oscillators of the radiation. Like if it's a wave, something is oscillating, that's why you have the wave motion, right? So both of them are interfering, and that's why their frequency is changing. So Planck assumed that radiation could be subdivided into discrete chunks of energy called quanta. So he was the first person on earth to put forward the theory that light can also be explained as particles. He was the first person to give the particle nature of light. So he said that what this sentence means is that light or energy, electromagnetic radiation, is basically also made up of particles in the sense discrete particles, packets. Think of so the wave nature is like continuous like this. What Planck said was, oh, light can be divided into particles, and each particle he called quantum, one quantum of light. So quantum is basically Greek for countableness. Like that's where you get the word quantity from. Okay. So each particle is called a quantum, and all of these quanta is basically the plural of quantum. So discrete meaning separate chunks of energy or packets of energy. Each of these is called a quantum. Altogether, plural is quanta. And that atoms and molecules could absorb or emit energy in these discrete chunks and not continuously. So he said the explanation behind black body radiation is that first groundbreaking thing, light is actually a particle, not a wave. And second reason, or the justification for that is that the atoms that are there in the black body, they could emit only like energy as specific quanta, not as a whole wave in itself, and then it would emit it back. So basically it would take one energy packet in and then it would emit it out again. Okay. So it's taking one packet in, whatever, interacting with it, emitting one packet out. Take one packet in, emit one packet out. So that's what he said. Like that's how he gave the explanation for the black body radiations.
Ma'am, I didn't quite understand the previous one. Absorption and emission occur from an oscillator.
So this is what he said. Like oscillator is basically the term he gave for atoms. Okay. So that's what it says. That is the atoms on the walls of the black body. So what he's saying is energy is being absorbed and emitted, right? So the absorption and emission are basically occurring from an oscillator or the atoms. The atoms are the ones that are interacting with the electromagnetic radiation. That's what it says here. Yeah. So
And
this,
now,
yeah.
second one is subdivided into discrete chunks of energy.
Yeah, he's explaining this further. So first point he said was atoms are the ones that are absorbing and emitting light. How they are absorbing and emitting light is in the form of discrete packets. So discrete is basically like separate chunks of energy. He called these chunks of energy as quanta. That is why the whole this side of physics or chemistry is called quantum mechanics or quantum chemistry.
So oscillator, quanta, all that is the same as atom.
Sorry, come again?
Oscillator, quanta, all this means atom only.
No, quanta here refers to light packets. That's why it was groundbreaking. So till now, people went with the assumption that light was a wave, electromagnetic wave, but Planck put forward the theory that light is actually quantized, or it's actually like separate chunks of energy. It is not a continuous wave. Don't worry if you don't get this intuitively. Like quantum mechanics is difficult for a reason, and especially at this level, like you guys are just starting grade 11, right? A lot of tools that you need, a lot of physics related concepts that you need to understand this, you haven't done it yet. You haven't started mechanics yet. So don't worry, don't beat yourself up if this is not making sense. I'll tell you guys exactly. I'm trying my best to make you guys visualize this, like understand this, and I'll tell you exactly what you need to note down and what you need to remember. Okay.
This black body experiment in the syllabus.
Yeah, all of this is there in the syllabus, but you will not get any theoretical questions on this. So I will tell you what questions you'll get. Like all of this is just for understanding.
So you won't be like asked to explain how he got the
No,
result.
you won't. There's a lot of other things to ask in this chapter. That part you won't get. Okay. So even if you're not, yeah, Rishad. Yeah.
Yeah, ma'am. So I wanted to ask. So you told I think atoms absorb the particles, right?
Yes.
So which atoms of the body, or I don't know, the light
Of the body
particle?
only. Like so, basically, atoms make up everything, right? So the point is that whenever light falls on a particular body, that body is made up of atoms. Now the atoms present in the body is what is going to interact with the light. Now how they interact with the light is they absorb light in the form of specific quantum, like discrete chunks of energy, and then they emit it back.
So why is the wave theory not correct that the lights are made up of waves?
Because if you go by the wave theory, like wave is basically, it's like a continuous thing, right? Like that's what defines a wave. Like you have a continuous, it's a disturbance that is continuously traveling throughout like a medium or whatever. But that does, like if you want to, so if an atom has to absorb it, like the absorption and emission should be like continuous, like whatever it's absorbing it should like emit back, but that's not what is experimentally fitting in with it. So atom absorbs all the light. Some wavelengths are emitted in like a large amount, that is high intensity. Some wavelengths are emitted in like a very small quantity. So like two things are not fitting, like the explanation is not satisfactory. The wave nature does not explain that. That is the reason Planck went with the assumption that, okay, what if it was not a wave, but if it was like individual packets? So this is like packet 1 of light, this is packet 2 of light, this is packet 3 of light. So that is what is happening here. So first there were findings, they did not fit with the existing explanation. So Max Planck proposed a new explanation for it, such that it fits the findings.
Excuse me, ma'am, we
So-
don't have to note anything yet, right?
Not yet.
I have another question.
Yeah.
So he assumed that the absorption and emission occur from the atom. So in a black body, it's kind of absorbing all of the light. What is it emitting?
So it won't keep it with itself when it is absorbing. So okay, just be clear. So absorption, if absorption happens, emission will always happen. So okay, I'll just tell you this. So let's say we have any random body here. Okay, when light falls on it, a few things can happen, like three things can happen. Some part of it is absorbed, which is basically taken in by the object. Some part of it can get reflected. So it's not taken in, it's just like reflected back. And some part of it can pass through. This is like, this happens only if this is transmission, and this happens only if this body is transparent, otherwise like nothing passes through. But whatever light is absorbed, it won't stay here. After being absorbed, it will get emitted again.
But in a black body, how is that possible? Because it's
so with a black body, because it is black and opaque, transmission does not take place. Nothing is getting reflected. Everything is going in, and then it's getting emitted as it is. I mean, not as it is. I mean, like whatever is absorbed will get emitted back. The main point is that nothing is getting reflected or transmitted through it. It takes in all of the light and lets it out. So that's absorption.
Why did Planck choose a black body for these experiments?
Because if I took a pink object, or like pink is complicated, let's say I took a red object, then we can see the object as red because it is reflecting back red light. It is only absorbing some of the wavelengths, which is the blue, green, yellow, all the other wavelengths. It is reflecting back red light, which is why we see it as red. But with a black body, it is not reflecting any light at all. That's why it's appearing black. It's absorbing all of the wavelengths, and it is emitting it out as like radiation. It's not reflecting it back.
Why do we need it to not reflect anything?
Because then your calculations, it's not complete, right? Like as per your assumption, okay, like if everything is being absorbed, everything has to be emitted, and everything, like whatever is absorbed, it has to be like emitted. Like let's say you're sending in certain range of wavelengths, then you expect all of it to be emitted in the same, what do you call it, like intensity that it's being absorbed. Like that's what the classical theory stated, but that's not what was happening. It was like getting repackaged somehow. Some of them were, some wavelengths were getting emitted a lot more than other wavelengths. That's what was happening there. That's why I took the example of red hot iron, blue hot iron. So the red, white, blue are not the natural color of iron. The iron ball is still black, but you can see those colors as a glow around it. That's because it is it's not normal light that's falling on it. It's absorbing because of its temperature. It is emitting that particular color. That's why it looks like that's the color of light that you see. It's not reflecting back whatever. See, there is a difference between an iron ball that is painted red versus a red hot iron ball, right? A red hot iron ball, you can see the red orangish glow even in the dark, but you can't see that with an iron ball that's painted red, because the difference is that for any color to appear, it needs to reflect that particular color back. But in the case of a red hot, blue hot substance, it is emitting its own light. So that's why I take care of the words. We're using the words absorbed and emitted, not reflected.
Ma'am, I have two doubts. So, one thing, what does black or any color transmit? So, you wrote transmission, right? So, what does it transmit?
Light. I mean, normal objects don't transmit light. This only happens when something is transparent, like your specs, like
But
windows.
I didn't get it. Like, what does it transmit? Light, but like what? Like how?
That, I mean, that's a completely different subject that goes into, properties of light. If you want, I'll look for a video and I'll send it to you, because I myself am not like completely sure of how the transmission takes place and all of that. Okay.
Okay, and it's the second thing. So, you told since it's not a wave, so it does not, do it. It does not
Again, be
happen
careful. I'm not
continuously.
saying it's not a wave. The wave nature does not explain it.
Okay, so
Yeah.
but basically it's not continuous. So, but still, if we use light, then when we see it back or get it reflected, but
Again,
we
not
see it
reflected,
continuous.
emitted.
No, but we are using a light here, right? So it gets reflected, no?
No, that's again, Rishit, that's what I was telling Kaveri also. Don't use the word reflected. Reflected and emitted means completely different things. So reflected is whatever is following is like it's not getting absorbed. Like reflected is the opposite of absorbed. But if you're getting light out of it after it is up, like it's taking it in and then it's emitting the radiation back, like that's emission. That's light being emitted.
So, ma'am, right now in today's times, how do we explain, like after this all these experiments?
Yeah,
Do we
after all of these, so the something called, have you heard of the term dual nature of light?
Yes.
Yeah, so dual
Yes.
nature is like two different natures. So both particles and wave nature is accepted. what is said in like scientific texts and all that is light behaves as a particle in some circumstances, behaves as a light as a wave in other circumstances. So it's both a particle and a wave. Like that's what is being said. And honestly, like I have not done research on it. Like even I have like studied it. So I also haven't completely, it's not there in my intuition, like going down to the quantum thing. Like I understand a lot of things, but it's not completely perfect for me. It's difficult, which is why quantum physics is kind of, yeah. It's hard to intuit, it's hard to visualize. Lots of analogies are there, lots of videos are there trying to explain it, but it's difficult, definitely. That's the reason classical mechanics, like motion of a car, motion of a ball, is explained very differently as compared to, motion of electrons or motion of alpha particles. Like things change at those scales. Okay. All right. But yeah, coming back to this, note these things down. The fact that radiation, or Planck's proposal or Planck's theory, is that radiation could be subdivided into discrete chunks of energy called quanta. So quanta is basically the plural word of it. Iska singular, like if you're talking about one chunk of energy, that's called one quantum of energy.
Ma'am, we only have to note what you underlined, right?
Yeah. So like you can add additional notes to it, like the things that I'm saying for your understanding. So quanta is like the plural, in brackets you can say singular quantum. So these particular packets, like each chunk of energy, is what people refer to as photons. So photons literally means energy particle. Like you have electron, like the particle associated with electricity, because electrons carry electricity. Proton, because again, that's another fundamental particle. Photon is basically photon, like light related particle. It's a particle of light.
That's quantum.
Yes, one photon is one quantum. Plural photons is quanta.
And at the time when Planck did all this, the structure of the atom was not clear as we know it.
No, it was not. So all this led to people figuring out the structure of atoms. Like, of course, people were aware that electrons existed, protons existed, but they didn't know how they existed.
But how did this experiment contribute to that? Like, yeah, okay, he concluded that there are photons and
we'll come to that. So this is not the only one. Like apart from this, you have something called photoelectric effect. Both together, using the concepts of both, you could study the spectrum of elements. So there's something called spectrum, line spectrum of elements also. So we'll touch on each of these subjects, like topics, after this one by one.
Excuse me, ma'am.
Yeah.
Is this Planck's observation or is this his theory?
Theory. Like he observed, he tried giving an explanation, and he put forward his theory. So the main thing that you guys need to take from this is the fact that, yeah, Planck, he's a very important guy. He was the one who said that light probably existed as particles. So discrete chunks of energy. So that's particles. And quanta or quantum is a name that he gave to those particles.
photons share the same structure as atoms, or they're different?
No, they're completely different. Atoms are again made of electrons, protons, and all of that, right? Photons are basically light. It's just pure energy. So if you're getting into structure of electrons, structure of protons, structure of photons, now that's like one level deeper. Like you get into something called quarks. Your Higgs boson particle, that the particle that was discovered or proved to be existing. It was quite recent, actually, 2016 or 2015. Till then, it only existed in theory, but you have CERN that has the LHC, right? Large Hadron Collider. So doing like, smashing particles in those, doing experiments and taking the measurements, readings and all. So they were able to prove that something called a Higgs boson particle exists. And this particle is what gives everything mass. Like what sets us apart from light, what sets apart this like pen from light is the fact that this has mass and light has no mass. So things that like matter, things that have mass also contain the Higgs boson particle. That. Anyway, that's like going deeper, different tangential to the subject. All right, are you guys done noting it down? Like, are you ready to go to the next part?
Just 1 second, ma'am.
Okay. Again, react with a thumbs up or put it in chat when you're ready. Okay, Arnav is done. Oh, 2 more people have. Sanat is done. Kaveri, Rishit, Adit. Okay. Shreya is also done. Okay, Ritu and Smera. Okay, Smera is done. Right. Ritu done? Okay, awesome. Okay, so we've established light can also exist as particles, discrete chunks, but light is a form of energy, right? So they have to have like an energy value associated with them. So Planck was also able to explain or give the value for that energy. So the energy of a quantum of radiation, like one packet, one photon, is directly proportional to its frequency. Makes sense? Frequency and wavelength are inversely proportional to each other. Hotter substances, more intensity, more energy means shorter wavelengths, meaning it should be higher frequency. Like wavelength and frequency run opposite to each other, like inversely proportional to each other. So he expressed the energy of a quantum in terms of its frequency. So he said E is directly proportional to frequency and introduce a constant of proportionality. So he gave the formula E is equal to h nu. So in this, E stands for energy of the photon, energy of the singular photon. Photon matlab one quantum, one energy packet. H is called Planck's constant. It's again a universal constant, just like your gravitational constant, just like all the other constants you have. So the value of Planck's constant is 6.601, I think, or 6.626.
6.626.
Yeah, into 10 raised to the power minus 34 joule second, and nu stands for frequency. Okay, this is an extremely important formula. We'll keep using this like a lot of times. Lots of problems related to this formula also. So we'll do a few numericals after this.
Could you, like you said, wavelength is this proportion? I don't understand that, like the formula.
Oh, do you guys remember the relation between wavelength and frequency?
uh,
Check your notes, check last week's
is
notes. And this.
C is equal to nu lambda.
C equal to nu lambda. So C is the speed of light, always a constant, which means that as frequency increases, wavelength should decrease.
Yes.
So wavelength and frequency are like running opposite. They're inversely proportional to each other, right?
Yes.
So like I was trying to put all of this together. So in our black body experiments, you saw that when we increase the temperature, the wavelength of the maxima was decreasing, right? As temperature increased, the wavelength, like red became yellow, then became blue.
Yes.
Yeah. So yeah, like which increasing temperature means increasing energy.
Yes.
So basically, as energy increased, the wavelength decreased, which means that the frequency increased. So energy is directly proportional to the frequency. Like it all basically just fits together that way.
Energy and wavelength are inversely proportional, and wavelength and frequency are inversely proportional. Therefore, energy and frequency are directly proportional.
Yeah. Don't say therefore. I was just like trying to show that it all fits. Yeah. So this was independently given by Planck. He just said that energy of a quantum is proportional to its frequency. Energy is directly proportional to frequency. Okay, noted this. Like note down what these three stand for also. E is energy of the photon. H is Planck's constant. Obviously, Planck discovered it, so it's his constant. Value of H is 6.626 into 10 raised to the power minus 34. Units are joule second. And frequency, like nu stands for the frequency. Okay? All right. So if you don't have frequency, if I give you only wavelength, can you find the energy of that particular radiation?
Yes.
Okay. So send the formula over chat. Like how do you do that?
Ma'am, could you repeat? Your voice got cut out a little.
Oh, so I was saying like this is the energy formula for calculating energy if you have the frequency. Now I said I did not give you the frequency. I gave you the wavelength of light instead. Can you calculate the energy associated with that wavelength?
No, wait, we need the speed for that, right? The
Speed is a constant. Speed is always like C is that only that one particular value, 3 into 10 power 8 meters per second. So H is a universal constant, C is a universal constant. These are not going to change in any situation in this universe. Smera, I said, like, I didn't give you the frequency. I gave you the wavelength. Kaveri, yeah, you're close, but I think you mistyped one particular thing. Ritu got it exactly right. Absolutely.
Ma'am, so we only have the wavelength, right?
Yes, you only have the wavelength. H and C, obviously you would have it because these are universal constants. These are not unknowns. So you can use them. No, Adit, that is not correct. You have two equations, you just have to put them together. So you know that E equal to H nu, also C equal to nu lambda. Kaveri got it correct. Nu is unknown. So how do you eliminate that from both these equations to get E, to relate E and lambda? Rishit, I mean, what you did in 2 steps, that's what I was asking you. You can do that in 1 step. That's basically it. So these are the 2 steps. So this I can rearrange it as nu equal to C by lambda. So this value nu, I can put it in this equation to get E equal to HC by lambda. So this is another expression or equation for energy. If you know the wavelength but not the frequency. If you know the frequency, use this directly. If you don't know the frequency, you can use this. Arnav got it, yes. He sent it before I did it. Counts. Okay. Simple, this is purely mathematics. So you have E equal to H nu. I don't know nu, but I know lambda. So find the relation, like how you can replace nu with lambda. I can do this with this formula, C equal to nu lambda. Rearrange it. So nu equal to C by lambda. So now I can replace nu in this original equation. So I get E equal to HC by lambda. So just after this, if you have done the working, fine. But if you haven't, note down the second formula also. The first is E equal to H nu. The second is E equal to HC by lambda. Note down both ways of finding energy. ठीक है? Okay, I'm clearing this. If anyone's still noting, let me know.
Ma'am, what's the speed of light, like the actual number?
3 into 10 power 8 meters per second. This we had discussed in the previous class only. Noted. All right. Oh, it's the same thing. Proportionality constant H is known as Planck's constant and has the value 6.626 into 10 power minus 34 joule second. Oh yeah, so this is what it means. So quantization of energy, like importance or significance or meaning of the formula is that energy equal to H nu, right? And nu is the frequency. So frequency is number of times a particular oscillation has occurred. So basically frequency, like I can't say that I oscillated half a time. Like obviously if I have a wave is completed only if the oscillation happened, like it's at mean position, goes to one extreme, the other extreme and back to mean, right? So frequency can always be a natural number. It can always be a whole, like a complete number. You can't have half an oscillation or 7/8 of an oscillation. So energy, the value of energy, like quantization of energy means that energy is always these many joules, or 2h joules, like 2 times h, or 3h, or 4h, or like 3 million h, or 4 billion h, right? You cannot have like 3.5 h. This does not exist. So energy can always take on discrete values in the form of nh, where n is any natural number. So that's quantization of energy. Yeah, h nu nh. Yeah.
But if H is in decimal form, then how can we always have energy as an
So
natural number?
energy, no, it's like saying, let's say you're buying rice, or no, rice is a bad example. What do you buy? So it's like if you're buying something like, say, chili powder from a shop, you can always get 1 packet of chili powder, 2 packets of chili powder, 3 packets of chili powder, right? The chili powder ka weight itself can be like a fraction. You can have 3.5 grams of chili powder, but you'll always get like 1 packet of 3.5 grams of chili powder, or 5 packets of 3.5 grams of chili powder. So it's always a multiple of that 3.5 grams, right? So similarly, h has a certain value. It's always a multiple of h. Energy can always take on a multiple of h. So that's why it's 1h or 2h or 3h or 4h, things like that. But it cannot take on value between them. Yeah.
Sorry, that doesn't mean energy has to be a natural number, right? That doesn't.
No, energy doesn't have to be a natural number. It is a natural number multiple of h.
Frequency has to be natural number one.
Yes, frequency has to be a natural number. Yeah.
Ma'am, I have this silly doubt, but what exactly does quantization mean?
Quantization means it's like energy exists as discrete packets. It exists as a countable thing. So that's what you get the word quantity from. Like quantum of energy is like a countable discrete packet of energy. That's why it's called quantization. Okay. Cool.
And what is J?
J is joule second. J is joules, the value. So how the units come is energy equal to h nu, right? Energy ka unit is joules, equal to Planck's constant we don't know, into nu ka unit, SI unit is 1 by second. So Planck's constant ka SI unit will be cross multiply joules into second. That's what Js is. Joule second. The unit of Planck's constant. Yeah. Okay. So we'll do some problems related to this particular concept. Okay. So look at question number 38. Neon gas is generally used in signboards. If it emits strongly at 616 nanometers, calculate the frequency of emission. So how will you do this? How will you calculate the frequency?
Energy by Planck's constant.
But you don't know the energy, right? Like look at what you're given.
Yeah, so we use the other formula,
Yes. So always when you come across a numerical, write down what's given. You're given lambda is 616 nanometers. Convert it into SI unit because you don't want to make a mistake there. So how will you convert this to SI unit? What should I write?
Ten to the power minus 9.
Correct. So it is 616 into 10 power minus 9 meters. So this is what you're given. Yeah, you need to find out what is the frequency of this. So which formula relates lambda and frequency?
C by lambda is equal to frequency.
Awesome. So C equal to nu lambda. So nu will be equal to C by lambda. Next, distance traveled by this radiation in 30 seconds. How will you calculate the distance traveled by this radiation in 30 seconds?
We reciprocate the frequency and we have the speed of light. So I guess we get the speed and the time.
You don't have to work with the frequency at all.
But time is the
time is 30 seconds. Time is like they've given you 30
Speed
seconds.
of light.
Yes, speed of light. So speed upon, what's the formula? Speed into time gives you distance. What is the energy of this quantum?
The E equals to Planck's constant into V wala formula we can use.
Very good, yes. So you can use either or, because you already found the frequency. Either you can use that, or you can use hc by lambda and use the wavelength given. Either way you can find out. Now let me clear it so that it's clear. The number of quanta present if it produces 2 joules of energy. Now what does this mean?
What is number of quanta?
So the wavelength that you're given, so this is the wavelength of one packet of that particular energy. Wavelength of one quantum. So the energy that you find out over here, right? So this particular energy equal to h nu is the energy of one quantum of energy. Like energy of, if you had one packet with a specific wavelength or frequency, it is the energy of that particular packet. ENERGY, energy of one quantum. Okay, so if the total energy is 2 joules, so this is how you figure it out. So one quantum produces this much energy, whatever you find out here, h nu amount of energy. If I have total of 2 joules, how many quantum is that? So it's like a unitary method way. Understood?
Yes, ma'am.
Ma'am, could you explain again?
Yeah. So this energy of the quantum, I'll call it E. Okay. So E equal to h nu is basically giving me the energy of one photon or one quantum. Okay. So this has, okay, calculate h nu and tell, or hc by lambda, and tell me what energy value you get here. Give me the number. You guys, for this calculation, right, like when you're doing it within class, you can use a calculator. But when you're practicing on your own, like once you got the hang of how to use the formula, then do the calculations on your own. Yeah. So how much, what is the value that you got here?
0.301 by 10 raised to minus 33.
Let's convert it into like, so whenever you give me an answer, I need like just, so I just quickly did it in the calculator. This is the value I got. So it is 0.0322 into 10 raised to the power minus 34 plus 8 plus 9 minus 17 joules. So this I can write it as 3.22 into 10 raised to the power minus 15 joules, right? Okay. So energy of one quantum is 3.22 into 10 raised to the power minus 15 joules. This is the value that we got. 15 नहीं, minus 19 होगा. Okay. Are you guys listening? Yes, sir.
Yes, ma'am.
Okay.
Yes, miss.
Yes, ma'am.
Yes, ma'am.
All right. So energy of one quantum is this value. Now, in that particular tube light, it's a neon light. Neon gas is used in signboards, right? So in that signboard, like if this is my signboard, the total energy that this board is giving out is 2 joules. So the light that is coming out of the signboard, there's lots of discrete chunks, like there's so many packets of energy coming out of the signboard, right? So all of these packets put together, I'm getting 2 joules of energy. And based on the wavelength, each packet is giving these many joules of energy. So what this is asking is, how many such total packets are there? Got it?
Yes, ma'am.
Kaveri.
Sort of.
Simple. Like E equal to h nu, say whatever you have calculated, that's the energy of one quantum. Like think of quantum as one packet, one energy packet. Okay. It produces, yeah.
Like one photon.
Yes, one photon, one quantum, like one packet. It produces 2 joules of energy. That's the total energy that the light is producing. So you're not getting just one packet out of the light. So there's like lots of little interactions taking place. That whole light is made up of a lot of small energy packets. So each packet is contributing this much amount of energy. You need to find out how many packets there are such that the total energy is 2 joules.
Okay.
Okay. So how will you find the total number of energy packets?
Also, ma'am, we can assume that they're asking a number of quanta. So can we take it like basically it's like the total energy produced like 2 joules basically upon the in the third whatever answer we got.
Correct. That's exactly it.
Okay.
That's what you have to do.
Are we supposed to use the calculators or we can just do it on the rough?
You can, I mean, this is like small numbers. You can do it either way.
Okay.
Can you find the frequency also, like stepwise? Like all the answers for this question 1, 2, 3, and 4.
Yeah, do it. I've cleared it. So all of you do each sub part of the question. So this basically covers all the concepts that we have discussed so far. So do it. So first, find out what is the frequency. Let's discuss the answer and find out what is the distance traveled and find out the energy and then find out the number of quanta. I'll also do the
So
calculation.
now we're using unitary method.
Yeah, the last part you'll be using unitary method. That's it. Okay, first part, frequency. So that's okay.
Ma'am, 616 nanometers would be how many meters?
Can anyone give the answer? How do you convert that to meters?
616 into 10 to the power minus 9.
Correct. Absolutely. Rishit, can you tell me what formula you used for nu? Also, guys, nu is a Greek alphabet. Spelling of nu, if you have to type it out, it is nu. Mu, I think you're familiar with. This is mu, mu. Nu, which is frequency in Greek, spelled nu. Yeah. It's not NEW. Yeah. All right, Rishat, no frequency, you shouldn't get that low of a value. Can you?
Basically, I just took, since we had the wavelength, I took that and the standard value constant,
Yeah.
and just I got that value which I typed it out.
No, then no. I mean, yeah, you have to take C and then given is the wavelength, but you didn't apply the formula correctly. So check again. So when your wavelength is in 10 power minus 9, your frequency, you'll get an extremely high value. You'll get it to the order of 10 to the power of, like 14, 15, 16, like that, those kind of values. That's a good hack. Like when you do the calculations, if you're not getting that kind of value, you can figure that, oh, I have to check my calculation again. Kaveri, yes, frequency, you got the right value. Yes, absolutely. Let me do it. So distance equal to Adat. Yes, Adat has expressed it in like the most correct way. Very good. But your unit is wrong, Adat. Frequency ka unit kya hai? Numerical, the number is correct. Your unit is wrong.
Is it not seconds?
No,
Hertz,
frequency.
hertz.
Hertz, yeah.
I made a mistake. So what I did was actually lambda in by the constant and not constant by the
Yeah.
lambda.
Yeah. C is not constant. Yeah, it is a constant value, but that's speed of light. Call it speed of light, okay? Or just call it C. Because if you say constant, there's like Planck's constant. Eventually, you'll come across universal gas constant and, a lot of constants. So don't call it constant. Ritu, yes, frequency is right. Kaveri got the distance correct. Rishit, yeah, now you got the speed of light correctly. Adit and Rishit have expressed the frequency in the exact way, like most accurate way, I should say. Third is energy.
We have to use the whole thing, right? 6.626.
Yeah, like you can go up to 6.62. I mean, if you're using the calculator, use the whole thing. Smera frequency is right. Smera has also expressed it accurately.
Ma'am, do we have to convert the second answer to nanometer also?
Second answer, you won't get in nanometers. You'll get a really large value, but not necessary. Meters is fine. Adit,
Oh,
again,
no.
you're getting confused by your units. Second one, you're
But,
finding out the distance, not the speed.
oh, so it's meters
Yes.
only. But is the answer correct though? Because I'm not sure.
Numerically, yes, that's correct.
Okay.
Kaveri, that's for the third one. That is not the correct answer. I'm guessing you got the difference in value because like we've taken very approximate values. Let's see. Smera, second one is right.
Ma'am, what's wrong with the third answer that I gave?
So your order is correct, like 10 raised to the power, that, but the specific number that you got is not correct.
Okay, I'll check.
I mean, it could be correct because, like for the frequency.
And I multiplied the correct ones. I don't know.
I'm not sure because it also depends on how much you approximated. Like frequency, since you've taken 0.004, that could change the value, but I don't think you should get that big of a difference.
I'll take more decimals in.
Just do it quickly, like on the calculator and see. So if you get the value, like okay, otherwise check the formula. Ritu, oh, you took a completely different. Okay.
Is it correct?
Yeah. Did you take speed of light as 2.99 something?
No, I took 3.
Oh, then it is not correct. It's a very
Ma'am, I did a rough
straightforward
work
value.
right now. For the third one, I did rough work, so there's no calculator.
Yeah, your numerical value is correct. Kaveri, yes, now your decimals are correct. You got it. But 10 raised to the power, I'll have to check. Let me just quickly verify that.
Oh,
Smera,
no, because
no.
34 plus minus 32 plus 11.
Minus 17, right?
To 10 raised to the power. Yeah, Adit, who sent 10 raised to the power minus? Yeah, Adit, your third is completely correct. Absolutely right. Smera, there's a slight.
So what's the number then?
What's the number in the sense? Your answer is completely correct, Adit. And Kaveri, yeah, now the number that you sent in, the decimal value, that is correct.
The power.
I'm in the second one.
Second, I have not received it yet.
No, I rounded off like the frequency to 0.4. So that be the reason I got like such a value.
No, you don't use the frequency, Ritu, for the second one. You don't have to use the
Oh,
frequency.
okay.
Yeah, Rishit, you got the second one. Smera, close but not. Yeah, Smera, you got it. Yes, the second time that you sent is right. Yes.
So, ma'am, in the third one, the 10 raised to the value, what is the value then?
So that, I
Is
mean,
it
it
10 raised
depends
to, is
on
it
whether
20
you
or?
took 32 or 0.3 or 3.2. I'll write the answer here because quite a few.
Planck's constant is minus 34, right?
Minus 34, yes. So the third one, if
17,
you
so
round it off to 3.22, then you'll get 10 power minus 19. So a few, like Aditya, you took 32 point, so you should get 10 power minus 20, that's right. And Kaveri, you took 0.322, right? So you should get 10 power minus 18. Okay. So Ritu, if you're still stuck on the second one, distance
What form?
traveled.
I think I used the long formula.
What did you use?
I used wavelength into frequency into time.
I mean, that is technically correct. But wavelength into frequency is speed of the radiation, right? So you can directly take the value 3 into 10 power 8 and do into time. Yeah.
Ma'am, I have a doubt.
Yeah.
You said it should be 10 to the power, if since I got 0.322, that should be minus 18, but I got minus 17.
If you just purely multiplied, didn't do anything else, then you should get 0.0322.
But even if I change the multiplication, the powers will still remain the same, right? So
yeah, no, see, like I'll tell you what. So the value is, if you just take 6.626 into 10 power minus 34 and 3 into 10 power 8, and in the denominator, if you take 616 into 10 power minus 9, this multiplication 6.626 into 3 upon 616 will give you 0.0322, and then it will be into 10 power minus 70. So on shifting the decimal places, you get 3.22 into 10 power minus 19.
I got 3 upon 616 is 0.04, and that multiplied by 6.626, I got 0.3226 only. I'll check once more.
Yeah. So the first one's answer, a lot of you have answered it. It is 4.87 into 10 power 14 hertz. Yeah. So just the pure multiplication, you get 0.00487 into 10 power 8 plus 9. So that on shifting the decimal, you get 4.87 into 10 power 14. Rishit?
0.032 only, it's correct.
So Rishit, no, the last one again, I think you have done something to the division or multiplication. Yeah, I don't think you've applied it correctly, because each energy packet is in the order 10 power minus 19. If you're getting 2 joules, the total number of energy packets, you have to get like really, really large value. Smera, last answer you've sent in, let me check. Number of quanta, yeah, looks to be right. Let me do the calculation, verify that. Yeah, Smera, your answer is right. Rishit, yeah, now we got it. So the last one, you literally have to do 2 divided by the energy. So you'll get 6.2 into 10 power 19. So if I shift the decimal place, so 6.2 into 10 to the power 18 joules, or the joules name. This is these many number of quanta. Yes, Adat got it. Rishad, you got confused by plus minus shifting decimal
What's the
place.
unit for quanta? Is there any unit?
No, it's a number of quanta. Like it's
Oh,
like
okay.
saying number of pens or number of bottles, like that.
Got it.
Okay. Shreya, I have not received answers from you. You following? Sanat, I haven't received from you also, I think. Yeah, Shreya and Sanat. So 61 points, so 6.19 into 10 power 18. Kaveri, yes, last one is correct. Got it.
Number of quanta, so this is it, right? There's no
That's
unit.
it, no units for that. Ritu, where are you at?
I realized why I got them wrong. I took the wrong value of B. Instead of writing like 4.87 to 10 to the power 14, I took like 0.4 into 10 to the power 15, and all
Oh.
the consecutive answers were wrong.
Yeah, but like by a tiny bit, right? So that is why the rounding matters a lot. So that's why, like, just maintain this, that whenever you get a value, get it in the standard form. Standard form is 1 digit before the decimal, and 1 digit after the decimal is fine, but like it'll be more accurate, it'll be more proper if you have 2 digits after the decimal. So whatever value, yeah, Kaveri.
This you said for the answer, but if we've been given a question where there are a lot of decimal points, what is, do we take 2 or 3 to get the accurate
2.
answer?
2 is fine.
Because in this one, when I divided 3 by 616, I when I took the whole thing, only then I got 0.0322.
Yeah, 616, right? Like, because the whole value is given as it is. But for Planck's constant, see, the more decimal values you take, the more accurate answers you'll get. But being off by, whether you get 4.87 or 4.88 is not an issue. But if you're off by a lot, like if you get, instead of 4.8, if you get like 3.9 or 4.5, then that's like it's off by a lot. So little bit difference, like a lot of you have gotten 6.19. With the kind of values I took, I got 6.2. Like that much of a difference is fine. But if it's something like 6.15 versus 6.22, like that's a large difference. So it's like, yeah.
Excuse me, ma'am.
Yeah, Sanat?
Can you see the messages I'm sending?
I'm not getting any of your messages, Sanat. That's why I called out.
Wait, let me just rejoin. Let me
Okay.
rejoin. Because I've been sending the messages. I've solved all the questions.
Okay.
I'll just rejoin. Maybe it's a
Yeah.
problem.
Network, maybe. Shreya, what about you? Have you been sending? I mean, I have not received
Yes, ma'am.
from you also. So,
Ma'am, should I send all of them again then?
maybe just try to rejoin. Or I mean, like you can check it. Like if you're getting a different answer, let me know. We'll figure out why it's different. Or else you can speak your answer also. You can ask questions. So. Okay. So other than Sanat and Shreya, yeah, all of you have sent in. Okay, but now have you guys gotten the hang of like how to use the formula, where to use it, how the questions can be phrased, all of that?
Yes, ma'am.
Yes, ma'am.
Okay, that's good. So look at 39. We don't have to do that right now, but read the question and tell me how you're going to approach it. Like, do you know what to do with this question?
That's picometer, right?
PM is picometer, yes. What's the order with picometer?
The calculations are time consuming. You know,
Yeah.
which,
calculation. Yeah, that's why I warned you initially. That's why, like, use a calculator till you get the hang of the concept, because you don't want to, load your head with calculations and not pay attention to the concept. So for now, first 2-3 problems, use a calculator. Once you've gotten the hang of the concept, like once it's automatic, then yeah, do the calculations yourself.
Do we solve the 39th or
no, tell me how you are going to approach it. Ritu, what are you going to do with 39?
I can't figure out like what unit is the PM. Like this.
PM is picometer. So like turn back to the first chapter. You can refer to chapter notes of the first chapter. So you're given different orders, right? Like nano, femto, pico, atto, all of that. So that's just conversion. But you're given wavelength and you're given provide 1 joule of energy, and you're asked what is the number of photons. So how will you find the number of photons with this?
I'm not sure.
Okay.
I try?
Yeah, Kaveri, go ahead.
I'm not sure, but 1 joule divided by, so since we have the wavelength, from that we can find out the frequency. So 1 divided by the energy that we get, so that's H into C upon wavelength.
Correct. Very good. That's absolutely right. So, Ritu, what you're given here is, so you're asked what is the number of photons of light with a wavelength of this much. So you have light. Okay, this is a light source. So this light, it is emitting light of wavelength 400 picometer, 4000 picometers, sorry. Okay. So you're given lambda, which means that it is emitting photons and each photon's wavelength is this much. So from this information, you can find the energy of each photon, hc by lambda. So each photon is containing this much energy. So it's emitting a lot of photons. So all of those photons together are emitting 1 joule of energy. So if you have to find the number of photons, it's just like the previous question. So total energy upon energy of 1 photon. Clearer now?
Yeah, this makes more sense. Thank you.
Yeah. Yeah.
Ma'am, can you explain the 39th again? I didn't understand.
Okay.
Ma'am, just one thing. So, what exactly is the total energy? We don't know that, right?
We know that the total energy that is being provided is 1 joule.
joules, right? Okay,
Yeah.
okay.
Okay. So Sanat, so what's happening here is, so it just says what is the number of photons. So we don't know, we are asked what is the number of photons. Photons are basically light energy. We do know something about the light energy. They have a wavelength of 4,000 picometers. This is how much. They have a wavelength of 4,000 picometers, and that provide 1 joule of energy. So the situation here is that you have a light source. Just imagine this is a light bulb, okay? So you have a light source Now, we just learned, like based on Planck's theorem or Planck's theory, that light is in the form of discrete packets. You have energy chunks. So basically, this is giving out all these packets of energy, all this light. Now, each packet, if you take one sample of the packet, it has a specific lambda. That means it has a specific energy attached to it. Now, overall energy, like the total energy given out by this light bulb is 1 joule. It's providing 1 joule of energy. So we need to find the total number of packets that this light bulb is emitting such that they all add up to 1 joule of energy. So one packet is giving you hc by lambda amount of energy. So how many packets are required to make up like 1 joule of energy? It's just like the fourth part of the previous question, Sanat.
Okay, ma'am, I understood.
Okay. All right. Everybody got it? Because a lot of questions are of this type. So you need to understand, like if you haven't gotten it, let me know. We'll spend some time on this. Oh, Ritu, you already like started calculating this. Okay. Now I'll give this question for homework. So you guys can do that. So once you got hc by lambda, check your calculation, Ritu, because you can't get hc by lambda as like you can't get it in the order of 10 power 23. Check if it is supposed to be 10 power minus 23 or, like if your exponents you've taken it correctly or not. Because this is picometers. So that's 10 power minus 12 or
I found my mistake. I forgot to take.
Okay. All right. 40 is based on photoelectric effect. So again, 42 is again very similar. So if you see the question, in astronomical observations, signals observed from distant stars are generally weak. If the photon detector receives a total of these many joules from radiations of 600 nanometers, calculate the number of photons received by the detector. Does this make sense? Like read the question again if you have to. Shreya,
It's the last one, right?
number 42. Okay, who's gonna say how to do this?
May I try this?
Yeah, Smira, go ahead.
Yes, so we have been told that the total is 3.15 into 10 to the power minus 18 joules.
Correct.
And
yes.
We have been given
Another, this number is given. What is this?
The wavelength.
Smira, in case you are speaking, not able to hear you, got cut off at we've been given. Oh, and now you've muted. Oh no, Smira, what happened? No, Smera, yeah, like you were audible and then you got cut off in between. Suddenly got quiet. Yeah, yeah, yes, rejoin, yes. Okay. So in the meantime, yeah, Sanat, continue. So this is the total energy we've been given. Then
Then that's the wavelength.
600 nanometers is the wavelength. Okay. So
Smell.
how will you use
We can
this?
use the formula energy is equal to hc by lambda,
Correct.
because
And
the other values are constants, and then we can find energy and then divide it using the total energy.
yes, absolutely. So if you use this in hc by lambda, you're going to get energy of 1 photon. And once you get energy of 1 photon, this is the total energy. Divide them to get the total number of photons. Okay, good. Okay, all of these are subsequent concepts. Yeah, I'm sure there'll be more questions, but yeah, these are the kind of questions that you can expect based on this particular concept. Okay. The next, another phenomenon. Okay, Shreya's joined back. Okay. So another phenomenon. So one is the dual nature of light. Like till now, everyone assumed light was a wave, but it was disproved, or not disproved, rather Planck discovered that light can be a particle also. That is one factor that that led or helped with the structure of atom. The next phenomenon that kind of led to or gave a hint of, okay, what is the structure of atom is photoelectric effect. This was again theorized by Einstein. Einstein played a role in developing the photoelectric effect. And this effect is what is used very, very widely in like everyday applications also. So it is due to photoelectric effect that solar cells work. So solar cells are used everywhere. They're there in your normal calculators, not your phone calculators, but like independent calculators. They're used in solar cells, like in space missions, because you can't keep giving electricity, right? So it needs a renewable source. So solar cells are an option because the sun is always there in the space. Lots of effects with respect to photoelectric effect. The main thing about photoelectric effect is self-explanatory. So if you look at the name, photoelectric effect. So photoelectric effect is the effect where in which electrons are ejected due to incident of light on certain metals. That's all it is. So basically step one, the photo part of it is if light falls on certain metals, or if when light falls on certain metals, falls on some metals like potassium, cesium, etc. Then the electric part of it, like because of this, electrons are ejected. So this particular effect is called photoelectric effect. Simple. So photo part of it is when light falls on some metals, on the surface of some metals. Electric refers to the fact that there are electrons ejected. How you can detect it, like how it is studied or found out, is that, again, this is the experimental setup. So this is the target material which is connected to the anode part of an electric circuit. You can see over here. And when light falls on it, so electrons are ejected, and electrons are ejected matlab they are ejected out of the surface of the metal. Like they used to be there in the metal and now they are ejected out. So if you have another surface to capture these like ejected electrons, and you connect it to a whole circuit, when there is no light, the circuit is not going to show any readings at all in the ammeter. But due to the incidence of light, suddenly it started showing readings in the ammeter. Do you guys remember what an ammeter does?
Measures the magnitude of current.
Measures the
Magnitude of current.
magnitude of current, correct. So that means due to the incidence of light, there is suddenly current flowing through this circuit. And current flows because there's like electrons that, there's like a potential difference, there's like a difference in charges. And that happened because there's like excess electrons over here and less electrons over here. So basically, that's how you can detect and study photoelectric effect. Simple.
Ma'am,
Yeah.
even before the anode reflected the electrons were already there, right? So even then the ammeter should have shown a reading.
No, that's what I was saying. Like initially, when there is no light, the ammeter is not showing any reading. Like it is set up in such a way that you just have the target material, like the metal that shows photoelectric effect here, and you have the cathode here, and it's just expected values, like nothing different. But without changing anything else, just because there is incidence of light, the ammeter starts showing readings. Now, why does the ammeter start showing a different reading? Like it shows that there is more electricity, there's increased value of electricity. Why that happens is because, like, okay, there's extra flow of electrons, extra current happening in the circuit. And where is that extra current coming from? Because of all the electrons that were ejected from the photoelectric material.
Is this the same Planck type property that it's absorbing and ejecting? Is it the same?
Yes, that's exactly right. Okay.
Do we have to note this?
Not. I'll show you. I'll tell you what exactly to note. So this is the main concept. This is like explaining what exactly is happening. Note down the definition or like explanation of photoelectric effect. I'll just find out where it is. Yeah. So note down.
Could you explain it once again? I didn't fully get it.
Okay, I'll explain it. Like we are going to study this more, but note down this particular statement. When certain metals like potassium, cesium, rubidium were exposed to a beam of light, electrons were ejected from them. So this phenomenon is called photoelectric effect. Note down this part.
Also, like in general, when we use to like an electrode, so it electrode. So anyway, there's always incident light on it, right? Or do we have to target it on?
Yeah, so getting into the finer details, like that's what we're going to get into right now. So note it down and then I'll take it forward. It definitely depends on, like what wavelength of light you're using and like all of these different factors. So we'll get into that now, like right now.
Okay. This only happens to these certain metals, not with.
Yeah. And you'll find out the reason. Like ideally, it will happen to all the metals, but
it's more visibly seen in these, maybe.
Yes. Like these metals are especially sensitive. You can figure it out easily enough. Like the examples that are given, what kind of metals are there? What is the common factor between those metals?
They're all from like the first, I'm not sure whether it was group or period, I forgot. I'm sorry.
That's okay. First,
but they're all from like the hydrogen line.
Yes. Don't count hydrogen in that family, but yeah, the sodium, lithium, that line. And
The metals.
alkali metals, yes. And what is special about alkali metals?
They're soluble in water.
Yeah, that's a property. But like, what are alkali metals? Yeah,
Highly reactive.
correct. They're highly reactive and they have a tendency to lose electrons easily enough. So this effect is like visible with alkali metals in the sense that it happens with visible light itself. But other metals that whose ionization energy are higher, like in which it's a little difficult for them to lose electrons, then you have to use higher energy light. You have to go to UV and X-rays and all of that. But yeah, we'll get into that eventually. Actually, you know what? It's almost 5, right? I'll continue with photoelectric effect in the next class. If you want, I can go over it like roughly, but yeah, if you think you're a little saturated, then I'll just do it in the next class.
I am
Can
a
you
little
solve my-
saturated, but I didn't get it. So will you like re-explain it, the whole thing next class? The
Yeah, yeah.
photoelectric effect.
Yes.
Thank you.
And ma'am, my sum.
Yes, I will discuss. Again, it's like in the decimal value, you were not able to get it, right? So just do the calculation again. I mean, method is not an issue.
I did, but I got the same answer again and again.
Okay. Can you send your working then?
Okay.
Yeah.
Ma'am, I had a question related to the last chapter.
Yeah, Kaveri.
Just a second.
3.27 grams of zinc and 3.3 grams of HCl. So yeah, just find out the number of moles and based on that.
It's like a textbook question. It's pretty simple, but I can get it. So we need to identify the limiting reagent.
Okay.
300 atoms of A or 200 molecules of B. So
One
can
moment. I'll just put it on the whiteboard. So you have 300 atoms of A.
And 200 molecules of B.
And what's the reaction?
We just need to identify the limiting reagent.
But Kaveri, without any reaction, there's no question of limiting reagent or excess reagent. There must be some reaction related to A or A and B. Or
A plus B2 gives AB2.
Plus B2 gives AB2. Okay, it is perfectly balanced. Okay. All right. So it is in a 1:1 ratio itself. A plus B2 gives AB2. You have 300 atoms of A and 200 molecules of B. Which one is there in a lesser quantity?
B.
I
But shouldn't it? I mean, so ma'am said that the answer should be like. I mean, I am confused. How can we compare atoms and molecules with each other?
The reason is that A is reacting as atoms. It is monoatomic. Like one atom of A reacts with one molecule of B. So that's the reason in this particular case, I can compare atoms and molecules. But
we need to multiply 200 into 2. So if that's where we get 400 atoms of B, so we can say that A is the limiting reagent, not B.
No, that's still wrong. Because if you have 400 molecules, like 400 atoms of B, right? Now, each atom of A requires 2 atoms of B. if you're looking at it, if you're converting it in that way. So you
How
have
to act?
A plus B2, right? Like each molecule is
Right.
made up of 2 atoms of B.
Yes.
Yeah. So that way 300 atoms of A requires 3 into 2, 600 atoms of B, but you only have 400 atoms there.
So even then, B is the limiting reagent.
Yes.
We can still do it this way and that way.
Yeah, it's just more straightforward because in the reaction itself, an atom of A is reacting with a molecule of B. So you can directly compare the atom with the number of molecules.
And ma'am, the stoichiometric coefficients, those can only be used to compare the number of moles, right? Not for atoms or molecules.
Number of moles, like if you think about it, it's the same. So the stoichiometric coefficients here are 1 and 1, right? If you're counting it at the atomic scale, like one atom of A is reacting with one molecule of B. But if I just scale this up, if I just multiply the whole thing by Avogadro's number, then that automatically becomes 1 mole of atoms of A reacting with 1 mole of molecules of B. So essentially, the number of moles is communicating to you the number of atoms and number of molecules itself, just that the scale is different.
So ma'am, if we always like doing stoichiometric reactions, we always do like if it's 1:2. So we do unitary method like that. But that way, by this logic, you can do it for anything, right? Atoms also, molecules also, anything.
Yeah, absolutely.
Then why do you always convert it to number of moles?
Because number of moles is like one standard convention. Like that way, the question that you just asked, like why can't I consider 2 atoms of B? Like why can't I consider the 200 molecules as 400 atoms? Like it gets rid of that kind of confusion, number one. And number two, if you're considering it in moles, right? Practically speaking, the number of moles will give you like it just makes more sense mentally. Like if I know that if I took 1 mole of carbon, then I can understand that it is 12 grams of carbon, as opposed to if I say I took 300 atoms of carbon, that's like an extremely small volume of carbon. Like I can't work with that practically. So practically speaking, if I need to know how much zinc I have to take or how much sulfur I have to take, working with number of moles will give you like workable quantities, because you can directly convert the number of moles into, the number of grams of that substance that you need to take, or the volume of that substance you need to take.
Got it.
Okay. All right. Somebody, yeah, Rishit, were you asking something like while I was discussing this with Kaveri? Someone had the question, Sanat or Rishit?
No, ma'am, I was answering, but then
Acha.
anyways, it's over.
Okay. Okay, cool. All right. So